Hello, future doctor. My name is Alex. Welcome to this high-yield science lesson on electrochemical cells. We have a couple of goals with this lesson, which pretty much all revolve around the idea of demystifying certain concepts. Potential, electrochemical cell, electron flow, these types of things. So if these are concepts that you're not entirely familiar with, there's a lot to look forward to in this lesson. In line with that, after this lesson, you'll be able to contrast oxidation and reduction potentials. You'll also be able to relate the mitochondrium to a type of electrochemical cell. And finally, you'll be able to calculate the MF, so the electron motive force, which oddly enough is not a force at all, given the reduction potential of two half reactions. Take some time to read this question stem. Here, we're told about the mitochondrium with its electron transport chain, where electrons are just passed from one compound to another, almost like a hot potato game. And then we're also told about some of these compounds. We talk about how NADH is oxidized first, which means that it loses its electrons to complex 1, which in turn loses its electrons to complex 3. And finally, we're given some standard potentials for NADH, cytochrome B, and cytochrome C. We have to use this information to find out the order in which these compounds are oxidized. So really, this will give us an opportunity to see why the mitochondrium works the way that it works, and how potentials can be used to quickly determine electron flow. Our first prompt really allows us to focus on the idea of potential. We're asked which of the compounds is given a different potential than the others. Let's look at the information from the question stem. We see here that the location of the electrons isn't always the same throughout the half reactions. That's to say, sometimes they appear on the product sides and other times on the reactant side. Let's consider the half reactions for NADH and cytochrome B first, since their electrons appear on the product side. Given the electrons' locations, are NADH and cytochrome B losing or gaining electrons in those half reactions? They are losing electrons. You can see here are starting compounds both becoming oxidized to NAD+ and the oxidized form of cytochrome B upon losing their electrons. Let's look at what this means in terms of their given values for potential. What sort of potential are plus 0.320 volts and minus 0.070 volts describing? They describe the potential of NADH and cytochrome B to be oxidized because they are associated with the oxidation reactions of both of these compounds. A great trick I have for you here is to think of potential as ability. Honestly, the moment I realized that ability is a perfect synonym for potential is the moment this concept clicked for me. Oxidation potential is the potential something has to be oxidized. In other words, its ability to be oxidized, or even just how good it is at being oxidized. With that in mind, based on these values, which compound would you say has the greatest ability to be oxidized between NADH and cytochrome B? It's definitely NADH, because it has a greater potential to be oxidized, as illustrated with its more positive oxidation potential. So that's another cool thing. When you ask yourself which compound has the greatest oxidation potential, it's the one that has the greater or more positive oxidation potential value. It works out just the same when you're looking at reduction potentials. The compound with the greatest potential to be reduced is the one with the greatest or more positive reduction potential value. So we've talked quite in depth about oxidation potentials at this point. Next time you're given a half reaction with an associated potential, the telltale sign that you're given an oxidation potential is if the electrons appear on the product side, which means that you have an oxidation reaction with an associated potential for that reaction to happen. So then, let's look at cytochrome C. Its electrons appear on the reactant side. This means it is being reduced, which again, we can see here with our little animation. Your reactants are the oxidized form of cytochrome C and the electron, and during the reduction reaction, the electron is picked up by cytochrome C, which becomes reduced. What type of potential is plus 0.254 volts describing? It's describing the potential that cytochrome C has to be reduced, and therefore is the reduction potential. So you know that you have a reduction potential when the electrons appear on the reactant side of a half reaction. So that's it. You have only two potentials possible. You can either be given a compound's oxidation potential or reduction potential. Here, we were only provided with the reduction potential of cytochrome C, which means that it was the half reaction to which a different potential was given. But is there any way that we can figure out the reduction potential for a compound if we're given its oxidation potential? Absolutely. You just have to flip the sign. That means that the reduction potential of cytochrome B, for instance, is plus 0.070 volts. Conceptually, this means that the better something is at losing electrons, the worse it is at gaining them, and vice versa. It wouldn't really make sense for something to be both good at losing and gaining electrons at the same time. Now that we have a decent understanding of the two possible types of potential and what they describe, we still have to figure out how to use them in order to determine which compounds are oxidized first. That's where this prompt comes in. We're asked how the reduction potentials of the electron acceptors following cytochrome C will compare to the reduction potential of cytochrome C itself. So looking at these three lines here, between cytochrome C, cytochrome A3, and oxygen, which of the following has a clear role in the electron transport chain? Oxygen is the final electron acceptor in the electron transport chain. It accepts 2 electrons and 2 protons to become water. In fact, notice that in water, the oxygen atom carries an oxidation number of -2 compared to in standard state when its oxidation number is 0. Being that oxygen is the final electron acceptor, how should its reduction potential compare to every other compound in the electron transport chain? We said that the reduction potential can be thought of as a compound's ability to be reduced. So oxygen's reduction potential should be the greatest because otherwise it would not be able to steal the other compound's electrons. Let's apply the same logic for cytochrome A3. If cytochrome A3 is the second to last electron acceptor, then its reduction potential should be greater than cytochrome C's but lower than oxygen's. So we see the trend here. In the electron transport chain, it's really the compound's reduction potentials that ultimately dictate the electron flow. We can right away use this conclusion to determine two things. First, we can already answer our original question, which is to say in which order will NADH, cytochrome B, and cytochrome C be oxidized. To be able to determine this, what should we convert all their given potentials to? This was a bit of a trick question. That's to say you can convert the three potentials to either reduction or oxidation potentials, as long as you're looking at the same type of potentials before answering the question. If you convert all the potentials to reduction potentials, you see that cytochrome C has the greatest reduction potential, followed by cytochrome B and then by NADH, which means that NADH is oxidized first, followed by cytochrome B and then cytochrome C. Alternatively, if you had converted all the potentials to oxidation potentials, you would have seen that NADH had the greatest oxidation potential, which means that it was oxidized first. The second thing this conclusion allows us to do is to compare the mitochondrion to a type of electrochemical cell. And I actually think that's a way cooler takeaway, so let's look at the mitochondrion right now. We have the matrix and the intermembrane space, which are separated by the lipid bilayer where the important complexes of the ETC are. So let's see how the mitochondrion acts as a galvanic cell by looking at the electrons flow within the ETC. You have NADH, which is going to give off its electrons at complex 1, and then you have FADH2, which is going to give them off at complex 2. In other words, NADH and FADH2 are oxidized in the matrix to give off their electrons. What component of a galvanic cell does this make the matrix equivalent to? This makes it equivalent to the anode, right? In any of the three types of electrochemical cells, essentially galvanic, electrolytic, and concentration, which is really just a type of galvanic cell, the oxidation always occurs at the anode and the reduction always occurs at the cathode. So let's follow our electrons from here. The electrons from complex 1 and complex 2 are going to be picked up by ubiquinone and brought to complex 3. And from there, they're going to make their way to cytochrome C, which is partly in the intermembrane space. Cytochrome C is being reduced, so we can think of the intermembrane space as being analogous to the cathode. So we see here the mitochondrion has compartments analogous to those seen in electrochemical cells, and electrons flow from compounds with lower to higher reduction potentials, which makes the mitochondrion analogous to a galvanic cell rather than to an electrolytic cell. Now I want you to think about this for a moment. What do you use galvanic cells for in real life? You use them to power your electronics. Batteries are galvanic cells. They power stuff because they give off energy when electrons are allowed to flow. That's opposed to an electrolytic cell, which you have to power to make it work. Then what does the mitochondrion use the energy given off by the electrons flowing? It uses that energy to create the proton gradient. So when electrons flow from compounds with lower reduction potentials to compounds with higher reduction potentials, the mitochondrion uses that energy to fuel the movement of protons from the matrix to the intermembrane space. And ultimately, this proton gradient is used to fuel the production of ATP. One last thing I think is worthy of mention here. So usually with galvanic cells, you have the anode and the cathode, which are separated and connected only by a metal wire. Why is that not necessary in our mitochondrion? Simply because the complexes are disconnected and the cytochromes and quinones sequester the electrons. This last prompt is not just an opportunity to make sure we've understood the two types of potential and what they describe, but also to find out how to calculate the electron motive force of a cell or a given reaction. We have a reaction where cytochrome C oxidizes NADH to become reduced. We also have two half reactions with NADH and cytochrome C with two associated potentials. Anytime you have to calculate the EMF, the first thing you have to do is know the types of potential you are given. In this case, what type of potentials are we given for NADH and cytochrome C? The electrons are appearing as reactants, which is indicative of reduction half reactions. This means we're dealing with reduction potentials. Now you notice here, we have two equations available to calculate EMF, which used to be the most annoying thing for me as a student. What's the point of having these two different equations to calculate the same thing? Honestly, there's not much of a point at all. Let's look at the equation on the left first. We see it uses a negative sign. What potentials are we supposed to plug in this equation? With this equation, we must use the reduction potentials for both of the compounds. The reason this equation exists is because most of the time, potentials are listed as reduction potentials. In fact, if you type standard potential table on Google and check out the images, most of the hits will exclusively give you reduction potentials. So even though it's not a reduction that's happening at the anode, we still use the reduction potential of the compound at the anode. So if we plug the appropriate signs, we find an EMF value of plus 0.565 volts. Now the second equation is the more appropriate equation, if you will, in the sense that it really highlights the fact that at the cathode, you have the reduction, and at the anode, you have an oxidation. So it uses the reduction potential of the reduced compound and the oxidation potential of the oxidized compound, and it just adds them up. So really, what's the negative sign doing in the equation on the left? It's literally just converting the oxidized compound's reduction potential to oxidation potential. The way I like to think about it is this. The equation on the left is saying, don't worry about converting the reduction potential, I'll do it for you. The equation on the right is saying, you have to make sure you're plugging the appropriate potentials. My biggest tip for you is just pick an equation and run with it. If you always want to use the one on the left, that's great. Make sure you're always plugging in reduction potentials. And if you always want to use the one on the right, that's great as well. Just make sure you're plugging the reduction potential for the reduced compound and the oxidation potential for the oxidized compound. But in the end, no matter which equation you use, if you use it correctly, it should give you the correct value for the electron motive force. Let's recap what we've learned here. We've contrasted oxidation and reduction potentials, which is a really important skill to have. We were also able to relate the mitochondrium to a type of electrochemical cell, specifically a galvanic cell. And finally, we saw how to calculate the EMF of a reaction by using two slightly different equations. I really hope this lesson was helpful in clarifying some of these concepts for you. Of course, this is definitely conceptually challenging material, so make sure to practice it often. But as always, try to understand these notions conceptually rather than simply trying to memorize them. You got this. Good luck.